Secondary sputtering lithography, or SSL, is a novel, non-traditional top-down nanolithography technique for the production of high aspect ratio and high-resolution nanostructures. It's a unique method capable of producing 10 nanometer scale nanopatterns in a simple and cost-effective way. Before looking at how SSL has advanced since its discovery in 2010, we'll first look at the principles of how SSL works. Then we'll go through the technical advances in SSL methods and processes and look at what that means for the future outlook of SSL. Secondary sputtering lithography is based on the concept of secondary sputtering, where plasma ions, such as argon ions, are accelerated towards the surface of a substrate. The physical impact of the ions causes particles on the substrate surface to essentially be torn off of the surface. The particles are then emitted at various angles with a wide angular distribution. The emission angle of the particles can be controlled by what the surface material is, the angle of incidence of the ions, and the accelerated voltage intensity which is applied to the ions. In SSL, a pre-pattern is typically fabricated on the substrate before the ion bombardment process. The walls of this pre-pattern act as a sort of template or base for the nanopatterns to form. Once this pre-pattern is fabricated and the ion bombardment process is complete, the particles which are torn off of the substrate will be uniformly deposited on the sidewall of this pre-pattern, as can be seen here. The etched surface target particles will essentially adsorb to the pre-pattern sidewall. Once these particles deposit onto the sidewall surface of the pre-pattern and connect with each other on that surface to form a 10 nanometer thick wall, a technique like reactive ion etching can be used to selectively remove this pre-pattern. After this step, you're left with ultra-high aspect ratio and high resolution 3D nanostructures after removing this pre-pattern. This novel SSL technique was first created by Jian et al. In 2010. First, in their fabrication, they started off with a silicon wafer coated with a 3 nanometer thick chromium adhesion layer. Then, using electron beam evaporation, they deposited a 30 nanometer platinum layer onto the silicon wafer. On top of that, a thin film of polystyrene, or PS, was spin coated on top of the platinum surface. The polystyrene line pattern, which can be seen here, is then made by making contact with a PDMS mold and applying heat. Once this line pattern is formed, the PS layer residual that remains on the bottom is removed by using RIE. After that's done, secondary sputtered particles are then attached to the side surface of the PS line pattern after the argon ion milling step is complete. So they get attached to the sidewall of the PS pattern. Then, the PS pattern remaining on the substrate is removed using RIE with a mixture of O2 and CF4 plasma, and then once this target material on the bottom is removed as well, you're left with high-resolution platinum line patterns over a large area. The authors also showed SEM images of various stages in the fabrication process. This image shows the step after the PS line pattern is made on the platinum-coated silicon wafer after applying a PDMS stamp. So you have your polystyrene pattern. Once the argon ion milling bombardment process is performed, the target platinum layer is selectively etched and simultaneously deposited onto the PS sidewall surfaces, as shown here. Once this step is done, the PS residual pre-pattern layer is selectively removed by performing RIE. So this layer is removed. And then you're left with high-resolution platinum line patterns. This shows a side view of the fabricated ultra-thin platinum line pattern using SSL. And as can be seen, the line pattern fabricated is approximately 17 nanometers wide and 75 nanometers tall, with a spacing of 500 nanometers between each line. This demonstration by the authors truly showcased the potential of the method for fabricating ultra-high resolution and high aspect ratio 3D nanostructures over a large area. This novel SSL method developed by Jian et al. Also has many key advantages. First, compared to photolithography, where fabricating 10 nanometer nanostructures requires complex equipment with high process costs, this method allows for making 10 nanometer nanostructures for less than 1,000th of the cost. Also, this method allows for a high aspect ratio of greater than 10 to be easily achieved because in this method, the height of the nanostructure only depends on the height of the pre-pattern, which can be easily changed by changing the PDMS mold and RIE conditions. Therefore, a broad range of feature sizes can be easily achieved. Additionally, this method allows for these 3D nanostructures to be made over a large area in a short amount of time. Lastly, the researchers also showed that this method is compatible with most polycrystalline metals and semiconductors, and they showed this by fabricating similar line patterns using platinum, zinc oxide, and aluminum to show that the method works with other materials. This is because instead of chemical reactions, the method relies on the physical impact of the plasma ions into the target substrate material. And so using this physical etching process, which implies a low etching selectivity, it means that this method is theoretically applicable to all or most materials. To capitalize on these advantages and continue the development of this method, many researchers have built on this SSL technology since 2010. This has led to many significant technical advances in the development of the lithography method. Through leveraging the fact that SSL can be applied to many materials, researchers have also developed SSL-based polyelemental nanolithography, where multi-component pattern nanostructures on the scale of 10 nanometers can be fabricated. In this method, developed by Jung et al., they first used polymer nanoimplant lithography to fabricate a polystyrene pre-pattern with a height of 400 nanometers and a pitch of 2 microns. They then sputtered each target component on the pre-patterned substrate. After performing argon ion milling and inducing the secondary sputtering process, the materials from the surface were sputtered onto the sidewalls, as you can see here, and formed the nanostructures on the sidewalls of the polystyrene surface. It should be noted that during this argon ion bombardment step, the target multilayers, shown as layer 1, 2, and 3 here, are automatically uniformly mixed. So as you can see, the materials are sputtered one by one onto the surface. Then once the argon ions go through the ion bombardment process, the materials are torn off the substrate one by one, and as a result they are mixed together and then deposited onto the sidewall surface. After this step of depositing onto the sidewalls, the polystyrene pre-pattern was removed by RIE, and they were left with extremely thin 10 nanometer polyelemental nanostructures, as you can see here. In this case, the three materials they used were gold, palladium, and nickel, but this could have been done with using many other combinations of materials. Through performing SEM, they were able to reveal the gold, palladium, nickel trimetallic nanopatterns with a pitch of 1 micron. They also performed scanning transmission electron microscopy and other methods like HADF, STEM, EDS to produce elemental mapping images showing that the cross-section of the line pattern does contain all three metals. Additionally, they found that the physical ion bombardment step did indeed lead to uniform good mixing of the metal components, as it could be seen that the metal elements completely and uniformly overlapped throughout the line morphology. So, all three materials were mixed well in the final structure. In addition, they also showed that they could modify the composition and thickness of the multi-component film on the substrate to ultimately control the internal structure of the final 3D nanostructures which are fabricated. They first formed a layered structure through depositing 10 nanometers of gold, followed by 10 nanometers of nickel, and then palladium on the substrate. Then, after the SSL process, a layered nanostructure with the same top, middle, bottom sequence of palladium, nickel, and gold was observed. since argon ion bombardment only allows for a penetration of around 10 nanometers, making each layer 10 nanometers thick allows for the same layer pattern to be retained. In the second structure, they initially deposited 9 much thinner layers following the repeating sequence of gold, nickel, and palladium, and each layer only being 3 nanometers. Then, after SSL, they noticed that this resulted in a mixed nanostructure, as the argon ions were able to penetrate deeper into the multiple layers because each layer was only 3 nanometers, and this led to the mixing of the materials. Lastly, the formed core shell inner structure which they made by depositing 5 layers on the substrate is shown here. They deposited these layers in the order of gold, nickel, palladium, nickel, and gold, and the resultant nanostructure exhibited this core shell structure with the same sequence of deposited metal layers. In general, they showed that multi-metallic nanostructures with tunable mixed structures could be developed. In addition to composition, new advances in SSL have allowed for the development of more complex nanostructure shapes to be fabricated. Researchers found that through controlling the fabrication conditions, the pre-patterned shapes can be controlled, which will ultimately control the fabricated nanostructure shapes and allow you to form any shape that you want. In work done by Gian et al., they varied the polystyrene pre-patterned pillar shape by increasing the RIE times and varying the polystyrene concentration. Increasing the RIE times varies the shape, and changing the polystyrene concentration or thickness varies the size. So initially, they deposited polystyrene onto their substrate and then applied a PDMS mold to get the pillar patterns. Then they performed RIE to remove the residual polystyrene layer at the bottom. They found that as the polystyrene layer at the bottom, as the RIE time was increased, this wide polystyrene bottom layer became etched to a greater extent than other areas. So as you can see, as the time increased, the etching at the bottom was increased as well. Now this was found because the unreacted etching particles typically aggregate near the bottom of the polystyrene pre-pattern near the gold surface, which induces further etching of the polystyrene bottom. So after they completed the secondary sputtering process, they found that because of these unique pre-pattern shapes, they'd fabricated various whole cylinder shapes of gold nanostructures. So these shapes had empty centers, and it makes sense as they were deposited on the sidewalls of these structures, and this results in these shapes being made of gold. This figure shows the SEM images of the fabricated polystyrene pre-patterns and the resulting high aspect ratio nanostructures with various complex shapes that were made. It should be noted that all of these shapes were produced from only a single master template, just with varied fabrication conditions. Along with the shape, novel techniques to control the structure of the conventional line-shaped pattern have also been developed by Jung et al. In this work, the authors developed tilted line patterns. So to make this tilted line pattern, they first deposited the polystyrene onto their ITO electrode. After applying a PDMS mold to generate the rectangular pre-patterned shape, they performed inclined anisotropic etching, so anisotropic etching at an angle, to generate the trapezoid-shaped polystyrene pre-pattern, where one of the sides of the pre-pattern is very vertical and the other side is inclined, as you can see here as well. So the inclination angle of the wall, they determined that by the incidence angle of the argon ions used for the anisotropic plasma etching. And then they performed the ion bombardment step by employing argon ions at an incident angle of 15 degrees relative to the trapezoid-shaped pre-pattern, as you can see here. Now, since the vertical sidewalls are both sputtered and etched, as you can see, the material is both sputtered and etched here because of the incident angle of the argon ions. Therefore, nothing actually deposits onto the vertical sidewalls, nothing remains. Material does remain, however, on the inclined sidewalls as the ITO is sputtered onto those surfaces. But it's not etched, only sputtered onto those inclined surfaces. Now, after applying this step, the polystyrene pre-pattern is removed, and then you're left with an ITO pattern tilted with respect to the substrate, as you can see here. The SEM image of this fabricated pattern shows that the inclined ITO lines are highly periodic over the entire surface. These lines are 15 nanometers thick, have a height of 300 nanometers, an aspect ratio of 20, and a pitch of 1 micron. Through employing this process using a variety of angles, they found that they could generate lines down to an angle of 60 degrees, after which the lines would become fairly unstable. The advantages and novelty of SSL allows it to be integrated very effectively into many applications. Specifically, gas sensors are one example of applications where SSL is used to fabricate gas sensors which exhibit very high sensitivities because of the high surface to volume ratio of fabricated nanostructures when you use SSL. Gas sensors typically work by inducing an electrochemical signal when the target gas interacts with the sensing channel, which is your nanostructure. In work done by Cho et al., they made a volatile organic compound or VOC sensor similar to a gas sensor by using SSL with copper oxide. Through applying the typical steps of SSL as we've covered before, polystyrene pattern transfer, sputtering target material, going through secondary sputtering to deposit onto the sidewall, and then removing the pre-pattern to expose your nanostructure. Through doing that, they fabricated a patterned P-type polycrystalline metal oxide semiconductor array with an ultra-thin, high aspect ratio. With this sensor, they were able to achieve very high sensitivity. Compared to a normal copper oxide film, the copper oxide channels, the nanopatterns, fabricated using SSL, achieved a gas response approximately 5 times higher when exposed to 1 ppm of hexane. This is attributed to the high resolution and small grain size of the P-type MOS structure they fabricated using SSL. In summary, we looked at secondary sputtering lithography and many advances in the method, including polyelemental nanolithography, using SSL to make complex shapes and structures, and how SSL is used to improve devices such as gas sensors. Although SSL has made great advancements, there are still many issues which must be solved to broaden its applications. As SSL has structural limits of fabricating only 10 nanometer resolution and aspect ratios of up to 300 at max, further research must be done to fabricate nanostructures with resolutions below 10 nanometers and aspect ratios above 300 to improve its ability to integrate it into applications and be customized according to what it needs to be used for. Additionally, as flexible devices gain a greater demand, more research must be done to develop cost-effective roll-to-roll techniques to be able to use SSL on hard and soft substrates for flexible optoelectronic devices. As the SSL method continues to be developed and the demands for high resolution and high aspect ratio nanostructures continues to increase, SSL is sure to become more and more popular as one of the top methods for fabricating nanostructures. Thank you.